The simplest power series is if we just let that an coefficient, this number in front of the xn, just be equal to 1 all the time. And if that's the case, we end up with this power series that is just the x to the power n series. So we get 1 plus x squared all the way to x to the power infinity. This is really just a geometric series. And when x is between -1 and 1, that means it's a converging infinite geometric series. And this series is equal to the formula 1 over 1 minus x. So when I sum this all up, that polynomial expansion is going to be the same as 1 over 1 minus x. This is what we mean by these polynomial series can mimic functions. So this polynomial that we get is going to represent this function or mimic this function as long as x stays between -1 and 1. And what ends up happening is that the more terms I add to this polynomial, it gets closer and closer to the function 1 over 1 minus x. And because n can be infinite, we can make this function better and better and better, or give us values that are closer and closer to the values that we're looking for, as long as we increase the number on n, and we can do that infinitely because this n can go all the way to infinity. So we're going to look at first the function f of x equals 1 over 1 minus x. This is a reciprocal function. We have a vertical asymptote at 1. And what we're going to see is that when we do this expansion, this one specifically, when we do this specific expansion, we're going to see that this polynomial is going to match this function. And we'll see that it will only do it for the values that it will converge. So between the domain x is -1 to x is 1. So looking at the graphs of these, so notice that in red here, I have my function 1 over 1 minus x. That's a red graph there. That is the reciprocal function. You can see there's my vertical asymptote here, okay, at 1, and this is the reciprocal function. And I've given the first 3 terms of that polynomial series expansion. So 1 plus x squared. Okay, so that's going to represent, if you take a look at that, it just represents the first 3 terms of that polynomial expansion. And when we take a look at what's happening here, that blue graph is matching the red graph. Now, it's not a great match, but notice that it is matching exactly at the center, which is at 0. And between -1 and 1, it's kind of matching, and it's really matching really closely near the center at 0. But as we get to the edges, -1, notice that it is moving away. And same thing at +1, it's going off to, okay, this is going off because that's going to go diverge because this is going to keep on going, whereas that's going to never cross that vertical asymptote. So it's diverging. It doesn't really match at once we get outside the boundaries where the convergence is between -1 and 1 for x. And at the center, it's a really good fit. But as we move out to the edges, it gets to be a worse fit. Now, we can make this a better fit by adding another term to this. So we're going to go from 1 plus x squared, which is the one in blue still, to 1 plus x squared plus x cubed. So I've added a cubic term to that to make it a cubic polynomial. And again, notice that the green graph being the cubic, again, it is centered at 0. Okay, so it's really close fit. Both are close fits. And as we move out to the edges, okay, it diverges past -1 and 1. But notice that it's a little bit closer. Okay, this green graph, we compare the same x value, the green one is a little bit closer. It's a little bit better fit. Okay, notice again the green graph here is a better fit than the blue graph at that same x value. So as we add more terms to this, we're getting better fits. And this is something called the Weierstrass theorem. Okay, so the higher degree the polynomial, the better that polynomial will fit any curve. So again, we increase this one. So here I've left the cubic in, I've taken the quadratic out, and I've put in a fourth degree polynomial. So we go from 1 plus x squared plus x cubed. Now we've got an x4. So that orange graph, again, notice that it diverges past -1 and 1 because our series doesn't converge beyond that. But if we take a look at some values of x here, it's really close here and not as close on the green. Okay, so you notice that the orange graph is going to be a better fit to the original red function because it's a higher degree polynomial. And the nice thing about power series is because it's an infinite power series, we can just keep on adding more terms and more terms to make it a better and better and better fit. And if we could do this to infinity, it will match exactly the graph, the red graph, all the way through to the interval of convergence. So all the way to -1 to +1, it'll be a perfect fit if we could go to infinity. Again, that's an if because we really realistically can't go to infinity. But for our purposes of accuracy, we could make it more and more accurate by just adding more and more terms of that polynomial. And we can do this indefinitely.